All right, so in line 17 here, I'm solving y, which is the solution of L times y equal bb. And if you go back to the notes, Ly is equal to pb, right? So you can say y is equal to L backslash pb, and that's what I have here. Y is equal to L backslash pb, which is basically bb. Right, so after this, at this point I have my y, and then I can go back and use this equation to solve for x, which is now u backslash y, because u times x is y. You can use x to be u backslash y, and here it is, u backslash y is going to be my x. So we can compare, let's say, this x compared to that x. And the goal is actually to show that these are identical. Okay, so let me just continue running this. Let me see, do it one more time. Let's get rid of this breakpoint. Okay, so let's compare. This is my first x, and here's the second x. And if you compare them, they're identical. Okay, so this exercise proves the fact that the backslash operator is nothing but LU factorization of the coefficient matrix and solving for y and then x. Okay, that's so all these three steps is so these three steps are squeezed into one operator called backslash. Okay, so I hope that makes it clear how backslash operator works. Now you can do actually LU factorization on any matrices, even if the matrix is not square. Okay, so during the error calculation we talked about the norm, if you remember that. So when we argued that the backslash operator for a rectangular matrix provides the minimum error solution, or the approximate solution which has the minimum error on all equations, we use the concept of norm. So I'm going to go back and show you what I mean by that. So here's the line. Remember we said the error is going to be ax minus b, right? And then to basically square every element of error and then get the square root of the sum, I use the function norm. So norm is nothing but well, you can think of in 2-dimension or 3-dimension is basically sum of squared, and then you get the square root of that. Okay, so this is called 2-norm. We have also a few other definitions for norm. We have norm p, where p could be any number, 1, 2, 3, 4, anything, or infinity. So if p is 1, it's called norm 1. If p is 2, it's called norm 2. And if p is infinity, it's called norm infinity, or infinity norm. Okay, so when p is 1, basically you get the absolute value of every element of a vector. So let's say x is a vector, xi is the entry, or is the ith entry of the vector x. So when p is 1, you're basically summing the absolute value of the elements. Okay? Basically this is when p is 1. When p is 2, you square them, you sum them, and then you get the square root of it. Okay, so this is called, I think it is also called root minus root. It's not mean squared, but it's the second root of sum of squares. Okay. Now when p goes to infinity, let's say p goes very, very large. And if p goes very, very large, then when we raise x to p power, right? And if p is large, from this whole sum, the largest xi will survive. And all other x can be discarded compared to the largest one. So this whole sum, okay, reduces to only one element, and that is going to be the maximum element. Okay, so and then if it actually provides the maximum, So then we have only one element instead of this sum, so x to the p power and then raised to the 1 over p, it actually makes it just xi. So what it does is if p goes very large, the result of this is going to be just the maximum or the absolute value of the maximum element. Or actually, the right way of saying this is maximum of the absolute values, like so. Okay, so norm is basically sort of like a measure or a metric to understand how large a vector is. Now, when we talk about norm in this class, you have to ask yourself, which norm are we talking about? It's like norm 1, norm 2, or norm infinity. Okay, at this point, we have 3 norms, and whenever I talk about norm, I definitely indicate which norm I'm using. Okay, so let's actually go back to MATLAB and do a little bit of practice there with matrix norm. So here is a script. By the way, all of these scripts are in Blackboard. If you go to Blackboard, there's a tab. Let me show you. There's a tab for scripts. So here is Blackboard. And let me just sign in. Okay, so it takes a little bit longer than normal. And I have to go to my courses. So che531, if you go to the course Blackboard, okay, where is it? Right here. I want to get the menus. Let's see, how can I get the menu? Not that one. Okay, so here's Blackboard, and there's a tab here called MATLAB scripts. If you click on that, you're going to see this. If I go to the student view, okay, so here is the student view of my Blackboard. I have to move it over here. Okay, so you go to MATLAB scripts, and you see that for week 1, I posted a couple of MATLAB scripts, the norm, introduction, and tutorial. I need to actually include the LU factorization. But anyway, so here is a short script to practice with norm. Let's say I have a 2. This is a vector. Okay. Let me actually start from the beginning. So the first line clears the screen, the command window, clear all, make all variables clear. Basically, it initializes all the variable to perhaps 0. If you rerun the code a couple times, right, every time you run it, the variables get some values, but then clear all makes all values basically vanish, or makes all variables equal to 0. All right, close all. If you have any plot or figure, then close all actually closes all the figures. All right, so now I'm creating a vector. So this is -4 colon. It's not semicolon, right? It's colon. Colon means, so that means create a sequence with equal interval. So from -4 to -1, if we put colon between the two, means go from -4 to -1 with increment of 1. Well, increment is inferred, is implied. It's nothing that we actually see it here. If the step size or separation is not included in this line, the separation is automatically assumed to be 1. Okay, so our x is going to be a sequence of numbers from -4 to -1 with separation of 1. So it's going to be -4, -3, -2, -1. So now let me just stop the code here. I'm going to put breakpoint right here by just clicking on this left margin and then go and run it. Okay, so there you go. So my x is a vector, it's a row vector from -4 to 1 with a separation of 1. Now I'm going to calculate norm 1, and the way you write it is norm x comma 1. It calculates norm 1. You can write norm x comma 2, like so. Or there's another form associated with norm 2, because it's very common. You can just call it norm x. So norm x and norm x comma 2 are the same. But for all other norms, you have to say what p is. So p is 1 here, here's 2, and here's infinity. Okay, so we say norm x comma infinity means this is infinity norm. Okay, so I'm going to put a breakpoint here, and because I do not have semicolon at the end of the line, you're going to see the result. Get rid of that none, and then just rerun it. Okay, so let's look at the norm. First, norm 1, right? So norm 1, if you remember, was sum of the absolute values. So 4 plus 3 plus 2 plus 1, that's 14. Am I right? Sorry, that's 10, sorry. 1 plus 2, 3, 3, 6, and 4, 10. And remember, that's sum of the absolute values. That's norm 1. The next line we have here is norm 2. So that means we have to square these, sum them up, and then get the square root of them. So this is 4 raised to the second power, 16 plus 9. That's 25 plus 2 plus 4. That's 29 plus 1 is 30. So norm 2 is going to be square root of 30, and that's about 5.4. Okay? And if you do not say 2, just say norm x, you're going to get the same result. So here's norm x. You see it's the same as this. All right, and then the last one is norm infinity. And by definition should give us the maximum element. Maximum in terms of absolute value. So it's going to be plus 4. Okay? All right, so the next thing we're going to look at is, let's say I have a matrix A, and so what we want to look at right now is, let's have a matrix A like this, and I change one element of it very slightly. Okay, I change it a very little, and then ask myself, what is the impact of this change in the overall solution? Okay, in other words, if I have a linear system, okay, so let's actually go to here. So let's say I have an equation ax equal b, and then let's say I have some uncertainty about b. Let's say you're doing some experiment and b is coming from the measurements. So if there's a little bit of error with the measurements, or your b has a little bit of variation, the question is how much we should expect x to vary. So given the variation in b, what is the variation in x? Okay, for this system of equation ax equal b. So to answer this question, we use the back// operator basically to solve the system, and then compare the two results. One is without this perturbation, and second time with this perturbation. Okay, so this is the initial coefficient matrix. Then here's my b. I can solve the system x equal a back// b. Fine. So at this point I have my x. Now let's change. Let's say in this case I'm actually changing b. I'm going to change b by less than 1% on the first entry. So instead of 4.1, let's say we put 4.11. Okay, so this is a less than 1% error, or less than 1% change in the entry of the first entry of b. The question is, if I change this entry by less than 1%, how much variation I should expect for x? Okay? All right, so we're going to take a look at this in the next part of this video, and then see the benefit of the back// operator as opposed to the inverse of the coefficient matrix. Okay? So stay tuned for the next part of the video on solving linear system using MATLAB. Thank you so much for watching.